Hello again. It's a pleasure to have you join us here. And let me just begin by recapping what we went over last time. So we went over this Nora problem instance, and I highlighted that you need to consider information that do not occur on any path between the source and target node to solve this problem instance. We also discussed why having to go off path to find information to solve a problem instance is particularly difficult for existing state-of-the-art models. Finally, I told you that in the Nora dataset that we curated, we have tens of thousands of examples, and in every example, we also have a proof like this one about how the query is solved. So this is useful if you want to do SFT and create high quality exemplars. I introduced this. We introduced this metric OPEC off-path edge count. So that's the number of edges that are required to solve the problem instances which do not occur on any path between the source and target nodes, which are part of the query. So this problem instance right here is one of OPEC3. One final thing about Nora I will comment on is that uh, the world rules that you use to find these hidden facts from the story facts are sort of intuitive and familiar to people. So this one, which says that Lee is an uncle of Rita and that means Lee is male, is something we're familiar with in our day-to-day experience. Likewise, this one, that Lee is male, Lee has no sisters, and therefore Jim, who's Lee's father, has no daughters. That's also something we would be familiar with. So Nora world rules are sort of grounded in our intuition. And that's also something important if you want to, especially if you want to adapt uh, large language models and induce some reasoning capabilities in them. So I'll show you some experimental results uh, that we did with Nora. And let's see, I think I want to get a bit better. There we go. So this one, so the top one is, so test topic is the one we're interested in. So, so this panel right here is how state-of-the-art models, state-of-the-art systematic reasoning models perform on this new kind of difficulty, which is OPEC. And this one is the performance of large reasoning models like O3 and O4. So this one is O3 actually. And you observe that when you have OPEC 0, so when you require no off-path reasoning, uh, O3 does pretty well, even when as you increase the number of reasoning steps required. Whereas when you start demanding off-path reasoning, the performance degrades very quickly. So off-path reasoning is not something that's theoretically difficult, but it's something which state-of-the-art models find difficult in practice as well. So the exact experiments, how they're set up, we discussed in the paper, and you can have a look at that. So it's quite enlightening how the experiments are set up and how we make it really a systematic reasoning problem. Okay, before closing out, I will tell you how so here you're observing that we are generating stories that have OPEC 12, so problem instances which have OPEC 12. So I'll briefly tell you how we generate such complicated stories and or such complicated problem examples. And I'll also tell you how we make the task a systematic reasoning one. And by that, I mean that the training examples are so constructed that they are simpler than the test examples, but also they are enough in the sense that if you're able to solve the train examples, you should also be able to solve the test ones. So let me show this to you here in this figure. This figure illustrates this fact. So these two problem instances are training instances. So here's the first one. Once again, the bold edges are the story facts. The query is, what is the relationship between Sam and Joe? What are the relationships between Sam and Joe? And this is a hidden entailed fact that we will need to derive in order to solve the query. So this one is solved as follows. Sam is a sister of Bill, so that means Sam is female. So Sam is a female grandparent of Joe, which means Sam is a grandmother of Joe. Now, Sam is the grandmother of Joe. Ty happens to be the maternal grandmother of Joe. So that means Sam must be the paternal grandmother. Here is a second training instance in Nora. Once again, so before I go to the second instance, let me just make one further comment on this first one. So to do this proof, we needed the help of two edges which were not on any path between Sam and Joe. These are these two pink edges. So this training instance or this training problem instance has OPEC 2. So that's its difficulty rating. Its difficulty rating is 2 in terms of OPEC. Let's go to the second training instance, which is this one. Once again, the bold edges are the story facts. And the query is, what is the relationship between Ty1 and Joe1? So here Ty1 is the wife of Bob1 and Bob1 has no sons. So from that you can conclude that Ty1 has no sons and Ty1 is female. So Ty1 is a female grandparent of Joe1, and since Ty1 has no sons, Ty1 must be a maternal grandmother of Joe1. So that's how you discover this hidden entailed fact, relationship between this hidden entailed relationship between Ty1 and Joe1, and that helps you solve the query. So these are two training instances. In Nora 1.1, test instances are formed by combining training instances or gluing together training instances. So here 3 is a test instance and it's formed by gluing together 1 and 2. So by gluing together, I mean, so you see, so what first we will do is we'll align the names in these two stories together. So we will combine these two stories by aligning these nodes. So Joe1 and Joe2 are glued together and made into the same entity. Likewise, Ty1 and Ty are glued together and made into the same entity. And then this story fact in the first story that Ty is the maternal grandmom of Joe. It's actually an entailed fact in story 2. So you can just delete this story fact, because it's going to be entailed. Once you combine those two stories, it's just going to be entailed. And that's how you get story 3. You glue these two stories together and you get story 3. And you change the names as well, because we always want to have unique names. We don't want our models to use the node names to solve the problem. Okay, so now you've glued these two problems together to get this one. And the query is, what is the relationship between Sam2 and Joe2? Okay. So the proof is basically you combine both the proofs of 1 and 2. So here is how it goes. So first you say Ty2 is the wife of Bob2. Bob2 has no sons, so Ty2 has no sons, and Ty2 is female. Female grandparent with no sons must be a paternal, maternal grandmother, right? So now you establish this Tai2 is a maternal grandmother of Jo2. Now you look at Sam2. Sam2 is female, Sam2 is a grandparent, so Sam2 must be a grandmother. So Jo2 already has a maternal grandmother, that makes Sam2 the paternal grandmother. That's how you find this hidden entailed relationship between Sam2 and Jo2, and that helps you solve the query of what is the relationship, what are the relationships between Sam2 and Jo2. So these two training examples had OPEC 2. So if you follow the proofs, you require these. So here you require these two pink edges, which are off path, to solve the problem. And when you glued them together, you got this test problem instance, and it had OPEC 4. So all these pink edges were used in the proof, and they lie on no path between the source and the target. So that's a benefit of gluing together small problems. When you glue together some small problems with small OPEC, you get you get problems with a much larger OPEC. And that's how we construct the test instances from the training instances. So this allows us to have test instances with very high OPEC. Also, it also guarantees that since test instances are formed by gluing together training instances, if a model can solve the small training instances, it should be able to solve the large test instances as well. Finally, this off-path reasoning is not the only kind of a, a new kind of difficulty or reasoning challenge that we discuss in this paper. We also discuss this two other kinds of challenges. One is reasoning. One is we sometimes create stories with ambiguous facts, and that's a new kind of difficulty. And we use this metric reasoning width to measure how much difficulty is introduced in a problem instance by introducing ambiguous facts. But I think I'll let you guys read the full paper to discover what these two things mean. Thank you for joining me. Feel free to reach out to me. This is my email. And yeah, I'd love to discuss reasoning and other stuff related to machine learning that's emerging. Thank you very much. Live long and prosper.